Hello friends, continuing with the chapter of communication systems, today we come to its seventh part, that is communication system part 7th. In this part we are to continue with modulation, and today we will study about pulse modulation. Now what is pulse modulation? Let us define. The process by virtue of which modulating signal is superimposed over carrier pulse and either amplitude, position or width of the carrier pulse is varied in accordance with the instantaneous amplitude of modulating signal, keeping other two constants. I repeat, the process by virtue of which modulating signal is superimposed over carrier pulse and either amplitude, position or width of the carrier pulse is varied in accordance with the instantaneous amplitude of modulating signal, keeping other two parameters constant, is defined as pulse modulation. Now look at this diagram. This is the modulating signal and this is carrier pulse. Now this modulating signal is superimposed over carrier pulse. Let us look into the next slide. So this is modulating signal and this is carrier pulse. Here modulating signal is superimposed over the carriers. Now here single polarity pulse amplitude modulation has been shown, where the amplitude of the carrier pulse is varied according to instantaneous amplitude of modulating signal. Here you see the two are in phase, so amplitude has increased. Here the two are out of phase, so pulse amplitude is reduced. Okay, so this is single polarity pulse amplitude modulation. If it is downward, if this portion is downward on the negative side, then it is double polarity PA, pulse amplitude modulation. Then this is double polarity pulse amplitude modulation. Okay. Now here in this part it is pulse position modulation, where you can see the position of the pulse is changed. Here you see this position of the pulse is changed. Here the position of the pulse is changed. Again here the position of the pulse is changed, and again here the position of the pulse is changed. The pulses are displaced from their original position. Now this is pulse width modulation. Here you can see the width has increased where the two are in phase. Here the width has decreased where the two are out of phase. Here also the width of the pulse is reduced because carrier pulse and modulating signal are out of phase. So this is how pulse width modulation is carried out. Here pulse amplitude modulation is carried out. Here pulse position modulation is carried out. Here pulse width modulation is carried out. Okay. Types of pulse modulation. Normally there are 4 types of pulse modulation. First is pulse amplitude modulation, PAM. Second is pulse position modulation, PPM. Third is pulse width modulation, PWM. It is also sometimes called as pulse duration modulation, PDM. Fourth one is pulse code modulation, PCM. So we'll take up one by one. First, pulse amplitude modulation, PAM. Let us define. The process by virtue of which modulating signal is superimposed over carrier pulse and amplitude of the carrier pulse is varied in accordance with the instantaneous amplitude of modulating signal, keeping other two constant, is defined as pulse amplitude modulation. I repeat, the process by virtue of which modulating signal is superimposed over carrier pulse and amplitude of carrier pulse is varied in accordance with the instantaneous amplitude of modulating signal, keeping other two parameters constant. Now look at this diagram. This is modulating signal and this is carrier pulse. Here modulating signal is superimposed over carrier pulse and here pulse amplitude modulation is carried out. This is pulse amplitude modulated wave and it is single polarity PAM. Okay. Now look here, where the signals are in phase, their amplitude increases, and where it is out of phase, their amplitude decreases. So you can look into the single polarity PAM. If this part is downward, then it is double polarity PM, that is double polarity pulse amplitude modulation. Okay. Now second, pulse position modulation, that is PPM. Let us define the process by virtue of which modulating signal is superimposed over carrier pulse and position of carrier pulse is varied in accordance with the instantaneous amplitude of modulating signal, keeping other two parameters constant. I repeat, the process by virtue of which modulating signal is superimposed over carrier pulse and position of carrier pulse is varied in accordance with instantaneous amplitude of modulating signal, keeping other two parameters constant. Now look at this diagram. This is modulating signal, this is carrier pulse. Here modulating signal is superimposed over carrier pulse and here we have pulse position modulation. You see in the diagram where modulating signal and carrier pulse are in phase, there the pulse is shifted towards left side, and where carrier pulse and modulating signal are out of phase, their pulse is shifted towards right side. So this is pulse position modulation. Third, pulse width modulation, PWM. Let us define the process by virtue of which modulating signal is superimposed over carrier pulse and width of the carrier pulse is varied in accordance with the instantaneous amplitude of modulating signal, keeping other two constant, is defined as pulse width modulation. I repeat, the process by virtue of which modulating signal is superimposed over carrier pulse and width of carrier pulse is varied in accordance with the instantaneous amplitude of modulating signal, keeping other two parameters constant. Now look at this diagram. This is modulating signal and this is carrier pulse. Now here modulating signal is superimposed over carrier pulse. Now look carefully on this diagram where the carrier pulse and modulating signal are out of phase, their width reduces, and where they are in phase, their carrier pulse width is increased. And similarly, on this side also, you can imagine where it is out of phase, width of carrier pulse reduces. Okay. Here also width reduces. Here also width reduces proportionately. Now fourth, pulse code modulation, that is PCM. Let us define the process by virtue of which modulating signal is sampled, quantized and coded into digital form, then superimposed over carrier wave, and either amplitude, frequency or phase of the carrier is varied in accordance with the binary codes of modulating signal, keeping other two constant, is defined as pulse code modulation. I repeat, the process by virtue of which modulating signal is sampled, quantized and coded into digital form, then superimposed over carrier wave, and either amplitude, frequency or phase of the carrier is varied in accordance with the binary codes of modulating signal, keeping other two constant, is defined as pulse code modulation. Now keying, if amplitude is shifted, it is called amplitude shift keying. If frequency is shifted, it is called as frequency shift keying, and if phase of the carrier wave is shifted, it is called as phase shift keying. Now block schematics of digital communication system. This is transmitter end and this is receiver end. In transmitter end, this is information input. Then we have sampler which samples the input, then quantizer which quantized the sampled pulses, then encoder which encodes the quantized signal. Now from this side there is carrier oscillator. The carrier oscillator generates a carrier wave which is given to modulator, and in modulator encoded signals are superimposed over carrier wave, and then through keying these are sent to communication channel. Now at the receiving end, these signals are intercepted and are given to demodulator. There is a local oscillator at the receiving end with the help of which we demodulate the coded pulses, and then there is a decoder, and finally we have information output which was generated at the transmitting end. So at the receiving end we have the information in its original form. Okay, so this is the block schematics of digital communication systems. Now sampling. How sampling of the information signal is carried out. Let us define sampling first. The process by virtue of which samples of analog signals are taken is known as sampling. Nyquist theorem. How frequently does an analog signal need to be sampled in order to reproduce it accurately is governed by Nyquist theorem. Now statement of Nyquist theorem. Analog signal is sampled at the rate equal to at least twice the maximum frequency present in the signal. I repeat, analog signal is sampled at a rate equal to at least twice the maximum frequency present in the signal. For example, look at this diagram. Sampling rate must be twice f2 because f2 is the maximum frequency in the signal. Over every 1/2 f2 seconds is sample be taken. So this is how Nyquist theorem suggests us how to take the samples. Now, analog signal to digital signal conversion. Now, suppose original signal be as shown in figure A. So, this is original signal. Its samples are taken as shown in figure B. Here we have taken the amplitude of the signal at various instants of time. Suppose here we take it as 1, here it is 3.2, here it is 1.9, and so on. Here it is 2.7, and here it is 3.2, and so on. So this is how we take the samples from the original signal. Now these samples are quantized as shown in figure C. So we round the fractional values, like if it is less than 0.5 we leave it, if it is more than 0.5 we increase it to the next number. Now here after quantization it is 1 already, 3.2 is 3, 1.9 is 2, and then 1.6 is again 2, 3.6 is 4, 1.8 is 2, 3.4 is 3, 2.1 is 2, 3.2 is 3, and 2.7 is 3. This is how we quantized the signal. Now the quantized samples are coded in binary codes. For 1 we write 001, for 3 we write 011, for 2 we write 010, for 2 again we write 010, for 4 we write 100, for 2 again we write 010, for 3 we write 011, for 2 we write 010, for 3 we write 011, and for again 3 we write 011, and then we convert it into waveform. Now this is 001, this is 011, and so on, and lastly we have 011, again we have 011. So this way all the samples, quantized samples, are converted into waveform. Match this quantized samples with the digital waveform. So this is how analog signal is converted into digital signal. Thus, analog signal is converted into digital signal and is used to modulate the carrier. Suppose this is a digital signal which is converted from analog signal. Now modulation techniques. There are 3 modulation techniques which are employed normally. First is amplitude shift keying, second is frequency shift keying, third is phase shift keying. Now here this is digital signal, this is carrier wave. Now here this is amplitude shift keying, this is frequency shift keying, and this is phase shift keying. Let us take up one by one. Now first, amplitude shift keying. Let us define the process by virtue of which amplitude of the carrier wave is shifted in accordance with the instantaneous value of the binary coded digital signal of the original modulating signal, keeping frequency and phase of the carrier constant. Now look at this diagram. This is digital signal and this is carrier wave. Now transmission of carrier wave is carried out according to digital signals. We say where we have the positive side of pulse. For 1 we send carrier, for 0 we do not send carrier. For 1 we send carrier, for 0 we do not send carrier. For 1 we send carrier, and so on. So this is called amplitude shift keying. Okay. Now second, frequency shift keying. Let us define first frequency shift keying. the process by virtue of which frequency of the carrier wave is shifted in accordance with the instantaneous value of the binary coded digital signal of the original modulating signal, keeping amplitude and phase of the carrier constant, is defined as frequency shift keying. I repeat, the process by virtue of which frequency of the carrier wave is shifted in accordance with the instantaneous value of the binary coded digital signal of the original modulating signal, keeping amplitude and phase of the carrier constant. Now look at this diagram. Here you see for one the frequency is increased, for 0 frequency is decreased, for 1 frequency is increased, for 0 frequency is reduced, and so on. This is called as frequency shift keying. Third, phase shift keying. Let us define first the phase shift keying. The process by virtue of which phase of the carrier wave is shifted in accordance with the instantaneous value of the binary coded digital signal of the original modulating signal, keeping amplitude and frequency of the carrier constant, is defined as phase shift keying. I repeat, the process by virtue of which phase of the carrier wave is shifted in accordance with the instantaneous value of the binary coded digital signal of the original modulating signal, keeping amplitude and frequency of the carrier constant. Now look at this diagram. This is digital signal, this is carrier wave. Now see here where 1 is there the carrier wave remains same, and for 0 its phase is shifted. For 1 it remains as it is, and for 0 the phase is shifted. Okay, for 1 carrier wave is as it is, and for 0 the phase is shifted, and this is called as phase shift keying. Now advantages of transmitting information in digital form. The receiver has to detect sample pulses which have the same shape and height. It has to recognize whether the pulse is present or not in any prescribed time interval. Thus, it is much less demanding task for the receiver as compared to detect analog signal, in which receiver has to detect as frequently as it can the many levels of varying amplitude of analog signal. Assignment 15 continues. Question number 25. A part, define pulse modulation. Give illustration for PM, PPM and PWM. B. What is pulse code modulation? How sampling and quantization is carried out. C. What is keying? Describe ASK, FSK and PSK, illustrating with diagrams. ASK for amplitude shift keying, FSK for frequency shift keying and PSK for phase shift keying. D. Draw block diagram of digital communication system. Now thank you so much. Here we finish with the chapter of communication systems. Next time we'll start with new chapter from optics. Till then, goodbye and good luck to you.